Hello everyone. I once again welcome you all to MSB lecture series on transformative chemistry. I am sure you are having good time reading chemistry and also enjoying life despite we have this COVID problem. Today I shall discuss about another important topic in coordination chemistry, especially when it comes to the substitution reactions of square planar complexes, that is trans effect. We all know that in case of square planar complexes, if we want to do substitution reaction, the preferred intermediate would be having a coordination number of 5, preferably having trigonal bipyramidal geometry. So, now let us see how this trans effect influences the entering ligand as well as leaving ligands while we perform substitution reaction. You know that as I already mentioned, when we perform substitution reaction on a square planar complex, the preferred one is expanded intermediate. That means coordination number having 5, and again the preferred geometry for that one is trigonal bipyramidal. So, in this one I have shown here X is the leaving group and Y is the entering group here, and in the intermediate what happens, one of the ligands and leaving group and also the entering group will form this trigonal plane and other two become axial or apical. And then once the elimination process is over, X leaves and it will revert back to a square planar complex. And now depending upon the type of complexes we have, we can see geometric isomers. Let us discuss now with this introduction, with this background, let us start looking into the trans effects. So, what is trans effect? I already defined in several ways. The trans effect is the labelization of ligands trans to certain other ligands, which can thus be regarded as trans-directing ligands. That means the labelizing effect of a ligand trans to itself or labelizing effect of a group trans to itself during substitution reaction to allow incoming ligand to a position trans to it is called trans effect. That means it is attributed to mainly electronic effects, important in square planar complexes and also observed to an extent in octahedral complexes. So, now as I mentioned earlier, we come across 3 class of ligands. You recall my discussion about classification of ligands by donor atoms. So, all ligands whatever we have at our disposal as coordination chemists or organometallic chemists, we have 3 types of ligands. One is pure sigma donor ligands. That means they have low energy filled sigma orbitals, they interact with metal orbitals to form sigma complexes. The other one is sigma donor and pi donor complexes. So, in this case we have low energy filled sigma orbitals and low energy filled pi orbitals on entering ligand, and these ligands would establish bonding with metals usually in high valent state, which are necessarily axophilic or halophilic in nature. So, that is called sigma donor and pi donor ligands. The third one is sigma donor and pi acceptor ligands. In those cases what we have is we have low energy filled sigma orbitals and high energy empty pi orbitals. So, they interact with appropriate metals to form this type of non-classical complexes. So, now all these 3 class of ligands would need 3 different type of trans theories to explain the substitution reactions. So, those 3 here are polarization theory, kinetic electrostatic theory and pi bonding theory. And of course, you should remember I did mention about the trans effect order. So, this is the trans effect series you can see here. For example, if OH minus is there, that can be readily replaced by NH3 and it goes like this. Now, let us try to understand one theory at a time and which theory is applicable for what class of ligands. Now, first is polarization theory. So, this was proposed by Greenberg, hence it is called Greenberg's polarization trans effect theory. Here you can see I have written 2 diagrams here. This is A diagram and this is B diagram. A diagram represents symmetrical induced dipoles in square planar complex of the type MX4. That means here all ligands are symmetrical and also we can see symmetrical induced dipole. You should remember, if they are neutral ligands and we have a cationic metal, according to crystal field theory, what the type of interaction we come across is ion dipolar interaction. Since it is based on electrostatic, so this is ion dipolar. So, according to that one, if you see, if we consider 4 ligands which are symmetric, then the induced dipoles will be symmetric in all 4 directions. So, in that case what happens, we do not have any preferred elimination of one of the ligand, any ligand can go during substitution reaction. On the other hand, if you have unsymmetrical induced dipoles at metal center, because of difference in the electronegativity of the ligands, then probably what we come across is unsymmetrical induced dipole that results in weakening of one of the bonds. So, you can see here in case of this diagram, we see 3 X ligands are there and one Y ligand is there here, and if we assume Y is stronger ligand, in that case what happens, it induces polarity or it polarizes the metal center also, and as a result metal will be having dipoles like this, plus and minus. If the stronger ligand would have positive, so that this bond is stabilized due to electrostatic interaction, minus and plus, whereas here this one will be having negative dipole pointing towards the ligand. So, here both are negative. So, what happens, repulsion starts, as a result what happens, this group starts leaving. So, this is called polarization theory, and if we just look into MX3Y, where the induced dipole of Y is greater than that of X, as a result what happens, this is how the arrangement happens, and then this bond is stabilized whereas this bond is weakened. So, this is ready for departure. So, this is the departing ligand, and once this is departed, so entering ligand would come and substitution reaction is complete. So, that means this polarization theory holds good for ligands such as ammonia, water, which are neutral ligands, neutral sigma donor ligands. I hope it is clear. Example I have shown here. So, water and ammonia, etc. So, fine. Now, let us look into another theory, that is called kinetic electrostatic theory. What is this one? For example, I have taken a complex like this, homoleptic platinum say 2 complex, and in the slow step entering ligand comes, okay, and it establishes a trigonal bipyramidal intermediate. As I mentioned here, during the substitution reaction, one group along with leaving group and entering group will form trigonal plane, okay, and other 2 will be axial. Okay. In the first step, X is eliminated. Once X is eliminated, what would happen is this trigonal pyramidal geometry will revert back to square planar complex. So, that means of course that it is a SN2 mechanism, bimolecular substitution nucleophilic, and both the availability of a vacant orbital, that is PZ, and the general accessibility of the central atom in square platinum 2 complexes makes SN2 mechanism very plausible, involving a trigonal bipyramidal configuration with the most electron attracting ligands are apical and the electron repelling groups are trigonal. This is very important. When we want to explain trans effect using the kinetic electrostatic theory, what we should remember is we have to gauge and analyze the nature of the ligands present on the metal before we form a trigonal bipyramidal geometry. That is, electron attracting ligand pairs are apical and the electron repelling groups are trigonal. So, that means if we have 2 negative ligands trans to each other, they are electron repelling groups, they will be trigonal planar. So, in the first step this happens. Now, let us look into couple of examples here. Recall how we made cis and trans platin complexes. We took first tetrachloroplatinate, added ammonia. When ammonia is added, so here there is no preferred leaving of any of the chlorides. So, since symmetrical, any one of these ligands can leave, and then NH3 comes, and again when you add another ammonia, so now ammonia is going to cis position here. So, this we observed, whereas on the other hand if you take tetramine platinum 2 complex, add chloride, again first one can go anywhere, and next when we add another chloride, it goes to a position trans to the chloride that is already present, that results in trans complex. Okay. So, now let us see whether we can explain this one in a more satisfactory way using kinetic electrostatic theory. kinetic electrostatic theory holds good for anionic ligands such as halides. So, now let us try to consider this trichloroamine platinum anion. So, now we want to add one ammonia. Before that one we should convert this into along with ammonia into a trigonal bipyramidal geometry. For that what we should do is we should remember this one: electron attracting ligands are apical and electron repelling groups are trigonal planar. So, now let us try to see which are electron repelling groups and electron attracting groups. Electron repelling groups are these two, both are negatively charged, and because ammonia is there you can consider relatively electron attracting group is this one. This is electron attracting group. Now we have entering group is there. So, with this one what happens now, this electron attracting ligands are apical. So, this one is, this should be apical. So, the moment you put apical, you know the fate of the isomer, what kind of molecule we are going to get, what kind of isomer we are going to get. So, now this will be here, this is coming here, apical or axial. Now, electron repelling groups are trigonal planar. So, these two chlorides along with ammonia will be forming this trigonal plane here. So, this trigonal plane. Of course, in the first step you should remember this is the slow step and this is the rate determining step, addition of ammonia. Now, once chloride goes, what would happen is already the fate of this molecule is decided. So, these two are there. So, basically when it comes back, this is going to be, see, anything in the plane is going to be cis to these groups here. As a result what happens, we are getting a cis isomer here. So, now let us consider the opposite of that one, monocationic triamine chloroplatinum. So, now it is very different. Electron attracting ligands are apical here and then electron repelling group because one chloride is there. So, this has to be in the plane, we can see here. So, this is has to be in the plane and this is in apical position. This is in the apical position now. So, now NH3 comes and of course, here plus is added, chloride is added. So, now once this ammonia is eliminated, now what would happen is it will revert back. Since we have two ammonia here itself in the intermediate itself we have in mutually trans disposition, we can always anticipate that we are going to get the trans compound, that is what exactly happens. And if you go back, same thing happened here, but obviously we had no explanation here. With better explanation came into picture because we have understood what is the trans effect and how trans effect is playing when we are using anionic ligands such as halides using kinetic electrostatic theory. So, what is important is this one should remember. When we are generating an intermediate having coordination number 5 with geometry trigonal bipyramidal, we should remember electron attracting ligands are apical, electron repelling groups are trigonal planar. We have to consider, we should not take literally meaning of this one. Among this pair of ligands which are electron attracting and which are electron repelling, we should see. If we have anionic ligand pair in a trans disposition, they are essentially electron repelling groups, and if we have neutral ligands or cationic ligands, probably they will be electron attracting ligands. So, based on this assumption, if we generate intermediate trigonal bipyramidal intermediate, obviously we can explain very nicely which isomer is going to form, and that is what exactly happens. So, this is kinetic electrostatic theory, holds good for anionic ligands such as halides. Now, let us move on to the third theory. This is called pi bonding theory. As name suggests, this holds good for substitution reactions having pi back bonding ligands. For example, if you have triphenyl phosphine, if you have carbon monoxide, if you have ethylene, such back or even N-heterocyclic carbenes, you can anticipate the role of pi bonding theory in the substitution reactions of square planar complexes. So, here I have mentioned again, you can see here I have written this trigonal bipyramidal transition state or intermediate, and now if you just look into this complex, and if let us say if we have a ligand here, this is capable of having back donation from the metal, and if we consider one of the orbitals say dxy, is the electron filled metal orbital that is ready for interaction with appropriate pi bonding orbitals present on the metal. So, it may be sigma star with tertiary phosphines or pi star with an heterocyclic carbene, carbon monoxide, cyanide and etc. So, the 3 ligands in the plane and the metal center can communicate electronically through pi bonding in the transition state or intermediate, this intermediate I am talking about. Okay. This implies that 5 coordinate species must be trigonal bipyramidal rather than square based pyramidal. One should remember, if L is a strong pi acceptor, like carbon monoxide, it will stabilize the transit state by accepting electron density that the incoming nucleophile donates to the metal center and will thereby facilitate substitution at trans to it. So, that means when the ligands are coming, you should remember ligands are always coming with a pair of electrons and they are looking for nucleophilic site. So, here in the pi bonding theory, how efficiently a trans directing pi acceptor ligand generates a vacant site, we are having less electron density at a position trans to itself. Okay, how to explain this one? Let us consider interaction of say sigma star or pi star of CO with one of the metal pi bonding orbitals, preferably dxy, dyz or dxz. Let us consider, since we have placed in this molecule in dxy plane, let us consider dxy, you can see here. So, here since it is a better pi acceptor ligand, so this electron density is moving. As a result, what happens, since entire electron density is pulled towards strong pi acceptor ligand, here what happens, here less electron density is left here. Here less electron density is left. As a result, let us say this is a leaving group and this is the entering group. What happens? This can leave, whereas this one is coming with a pair of electron and this is an excellent nucleophilic site. So, substitution is completed. So, this is how pi bonding ligands facilitate substitution at a position trans to itself. That means, first of all, by taking electron density, what happens, it leaves less electron density so that it can go, and then next one it is coming with a pair of electron, this is looking for a nucleophilic center, it generates nucleophilic center trans to itself, and once the substitution is over and this is eliminated, it would revert back to square planar complex with having appropriate geometry or conformation cis or trans, in case if there is a provision for isomerization or formation of 2 isomeric species. So, now using this trans effect, okay, let us see how we can make different all possible. So, let us see by using this trans effect how we can make some isomers. For example, if you consider this complex here, if you consider this complexity, this one is something like this A, B, C and D. So, all ligands are different, and it is a neutral complex, and if all ligands are different and also whatever the ligands that are present, I have also provided trans order for these things, and starting with simple metal complex of our choice, let us try to make, first of all we should know, when we have 4 different type of ligands in a square planar complex, how many isomers are possible. First we should make out that one. With this one we can have a maximum of 3 geometric isomers. Let us see how we can make or how we can prepare these 3 isomers using the trans effect order that is provided here, NO2 minus Cl NH3 and methylamine. Let me start with a complex of this type, the simplest one, having 3 chlorides and 1 NO2, and this is 2 minus. Now we shall add first ammonia. When we add ammonia, we should know where it goes, since NO2 is the strongest trans directing group among all. Obviously NO2 levelizes a group trans to itself, means this should say goodbye, this chloride should go, he has no option other than leaving that place. So now we have one negative charge. Now let us add methylamine. Now we should see where methylamine goes. Now we have two chlorides are there. Among chlorides, what happens? One of the chlorides should go. So we made one, this is one isomer. Of course, it is convenient if we write down first all possible isomers and then look for the preparative method starting from an appropriate substrate molecule or metal complex. Now what I would do is I would start with again the same. Now instead of adding NH3, what I would do is I would add first CH3NH2. When it goes to, the position does not change. In place of ammonia here, methylamine would go. So no change. Rest of the ligands would remain same at their respective positions. So now I shall add ammonia. Now ammonia can go here. So we ended up getting a neutral molecule. This is the second isomer. So we are left with one more isomer. For this one I can start with one of these compounds that we have already made. For this one what I would do is I would take this itself, this compound itself I shall take for that one. NO2 position remains same, chloride remains same. I am taking NH3 here and then here NH2 CH3. So now I am adding one more methylamine to this one, so that it becomes very clear where it is going. This would not change, and of course this is already there, this would not change. So this comes here. So now we have positive charge. So now we will add Cl. If we add, we should tell where it goes now. The next question is, if I am adding here, where it goes. Now just go back to this one. Among all, this is the strong NO2 minus is the strong transdirecting group. Obviously this chloride should go to a position trans to NO2. This is the third isomer. So now you know how effectively we have used this trans-directing series, and we have prepared all the three isomers possible for this combination of 4 ligands of general formula ABCD. So similarly it is very interesting, whatever the complexes you come across having ABCD or ABC or ABCD, of course in case of ABCD you can have 3, when you have A2B2 you can have 2 isomers. In these cases you just look into a combination of different type of ligands having different trans-directing abilities and try to familiarize with this trans effect series of performing substitution reaction. So let me take up another interesting example before I conclude trans effect with the square plasma complexes and move on to looking into the substitution reactions in octahedral complexes. Until then, have an excellent time reading and understanding inorganic reaction mechanism. Thank you for your kind attention.